In this work example, we're considering the question, an escalator in an underground station has 250 people standing on it and is moving with a velocity of 4.3 meters per second. The average mass of a person is 78 kilograms, and the angle of the escalator to the horizontal is 40 degrees. What is the minimum power required to lift these people? If we're solving for power, some students will immediately go to this force times velocity. So remember that that's an equally valid way to think about power. And if we're given velocity, it's probably the way that we want to think about it. Remember where this comes from. Power is work divided by time, the rate that work is done, or the rate that energy is converted, work and energy being the same thing. And work is still force times displacement, and displacement over time, the rate of change of displacement is indeed velocity. So that's where that comes from. If we draw 250 people that each have a mass of 78 kilograms, and I'm approximating them all as a block here, just like I did for the last one, the incline is 40 degrees. These 250 people have mass, and on Earth, they're going to have weight equal to mg. Some of the weight acts into the ramp, and the sort of the structural integrity of the escalator itself supports that. The power that the escalator has to sort of deliver to lift the people is to overcome this component of their weight, the component that would otherwise have them sort of roll down, right? And so when we think about what force are we going to plug into this equation, it's going to be not all of the weight, but rather the component of weight that's acting down the ramp. And so if that angle is 40 degrees, then this angle is 40 degrees, and the component of weight that acts down the ramp is opposite that angle. And so mg sine 40 correctly determines the force due to gravity that the escalator must provide. And so once we calculate mg sine 40, we'll have the force, multiply it by 4.3, and we'll have a number that we can compare to these. Now, our answer is going to be in watts, and all of our answers are in kilowatts, but it should be clear, you know, sort of what the correct value is. Don't forget that there's all 250 people standing on this escalator. So the mass is for all of them, 250 times 78. So we've got 19,500 kilograms worth of people on our escalator. And on Earth, there's 9.81 newtons per kilogram. And so like the weight of all those people is 191,295 newtons. But thankfully, only the sine of 40 degrees times that is the force that's needed by the escalator. So we'll multiply that by the good old sine of 40, which I know from my memorization of sine tables is 0.642787609, I think. And so that gives a force of 122,962. I also did that with mental math. I will now multiply it by 4.3 in my head and get an answer of, carry the 1, 528,736.8399, I think, thereabouts. Which I wrote underneath this answer because that's like 530,000 kilos. So choice C is correct here. Let's keep a good thing going and move on to a lift problem. A lift is an elevator, escalator to the elevator problem. An electric motor operating a lift has an output power of 20 kilowatts. The lift and passengers have a combined mass of 1,500 kilograms. The motor raises the lift through a distance of 20 meters, and we're answering how long does it take? All right, so power is force times velocity, like we just talked about. The force is the weight, mg. The velocity is the distance over time, and that must be equal to the power. If we do the old algebra switcheroo, then we can isolate t and realize that it is mass times the acceleration due to gravity times the displacement divided by the power, right? Multiply both sides by t, divide both sides by power, and the time that it's going to take is equal to all this. So let's plug in some values here. T equals the mass, 1,500 kilograms of people. G, 9.81 newtons per kilogram here on Earth. The displacement, 20 meters. And the power is 20,000, right? So it's 20 kilowatts given. So 20 1,000 watts. Now, a watt is a joule per second. And a joule, let's look right like this. A Newton meter, that's a joule. So a joule per second, the seconds go back up here, right? Those meters will cancel. Those newtons will cancel. Those kilograms will cancel. Nice, I'm in seconds of time. Remember, the units are a nice little sanity check on your calculation. Now it's just pushing some buttons. 1,500 times 9.81 times 20 divided by 20,000. And you get 14.7, which agrees with choice B, 15 seconds. Right? 14.7 seconds is about 15, so choice B is correct there. That was a power calculation. That was a power calculation. Question 17 is an energy problem. Let's take a moment to consider that. We got a boy on a bicycle rolling down a hill, 30 degrees to the horizontal. And we want to know the kinetic energy of the boy on the bicycle after they roll 20 meters down the hill. Okay. It tells us there's a frictional force opposing it of 30 newtons. So the path to the solution here could be using like equations of motion and trying to determine the velocity and then plugging it in here because we know the mass. But rather, we could use the law of conservation of energy, the fact that energy is neither created nor destroyed, to use an energy argument of this thing has potential energy up here. There are some losses due to friction, right? And so there's work done by friction. That's going to be equal to force times displacement. So remember, potential energy is mgh. We'll subtract away from that the work done by friction. Work in general is force times displacement. And that's where this sort of comes from, right? Potential energy is the force, that you have to lift something is its weight, and the displacement is the height, right? So like these are really the same equations. They're both measured in joules. So if we can determine the potential energy here, subtract away the frictional effects, then all the rest of it should be the kinetic energy, which will be our final answer. And we don't really have to know the velocity. In fact, once we know the kinetic energy, we could plug it in on this side and determine the velocity that way. The height of the boy on the bicycle is going to be equal to 10 meters. And I think that's clear to everybody watching this video why that's the case. Because you know that the sine of 30 degrees is a half and the hypotenuse is 20. So I'll just show you. Sine 30 equals opposite. The opposite side is the height. Not h for hypotenuse, but h for height in this physics calculation. The hypotenuse is the actual path that the boy on the bicycle traveled 20 meters. And so if you solve this for h, you get 10 meters. Now we can calculate the potential energy. 25 times 9.81 times 10. That gives you an energy of 2,452.5 joules. And immediately you could recognize that A must be the correct answer because there's no way we could have more energy than that. This is like an upper limit on the kinetic energy. Like it can't be more than that because we only have that much potential energy. They don't tell us anything about any other force that's speeding it up. So we know the answer has to be lower than this once we consider the frictional effects. The friction is 30 newtons times 20 meters, right? Force times displacement is the work done by friction. So it's going to be lost to the system. It's stealing away from the energy that it possessed potentially, at the top of the hill there. 30 times 20 is 600. And so 2,452.5 minus 600 is 1,852.5 joules. So choice A is correct. If you needed the derivation of these equations from the basic definition of work, make sure to click the link above. This has been another couple of work examples with Dr. Schleif for the midterm 2021, and we'll see you next time.